back. Last time and the time before that, we delve somewhat deep into how numbers can be implemented on a computer, and what limitations come from that, what possible sources of errors you should really keep in mind almost all the time when appropriate. Really, when you're developing big systems, it's really helpful to have a good model in mind to see how things really work. It's difficult because complex systems are really complex usually, and they rely on lots of complexity that you didn't make. They rely on complexity that's inherent in the system, that was made by somebody else before you, and so taking all of that complexity in at before you start working is impractical in many cases. There really are important cases where it's impractical. So one of the solutions to that is to start with a simpler model of how things work, and then as you get comfortable, as you cross that initial barrier, you can come back and really learn how things work, because when something goes wrong with the systems that you make, it can go wrong basically at any level. There's nothing that guarantees that the simplified model you carry in your head is enough to understand the sources of errors you will get even after 1 week of programming. It's possible that your first error that you encounter would take you several months of diving deep in how computers work just to understand how it happened. It's unlikely, thankfully, but it's possible. So that's why I kind of started with by no means exhaustive study of how numbers are implemented in a computer, but hopefully with enough juice to give you some idea of what can go wrong, hopefully what goes wrong in the simplest cases, and so that it's not too abstract or complex for you to really fully assimilate. Now we're going to talk about so-called numerical methods. All right. If you're a physicist, you know that it's hard to get much physics done without some basic notion of differentiation. I might be spelling that wrong. Integration, a bit of algebra, so a bit of probability, vectors. So these are mathematical concepts. in physics, they're not used in their own right. They're used as tools to understand and to represent how certain physical systems behave. And those are so-called analytical tools. Analytical methods. And similarly, without some basic discussion of some kind of methods to apply once our intuition fails us, we won't go very far. It's not to say you can't do physics without learning the numerical methods we're going to look at next. It is rather to say that computational physics can be applied in a broad range of physical systems. However, it's usually applied in systems where other physical methods fail. I'm not exactly sure why that is, but when we can apply simple analytical methods, we do so. And those are the problems we teach to undergrads in physics. Those are like the simple problems that teach you basic stuff about physics. For the problems where there are no simple analytical methods, or the analytical methods that there are so difficult and so advanced that you can't really expect undergraduate students to fully engage with these problems. These kinds of problems are the kind of problems we're going to be interested in. Problems that are really difficult from an analytical standpoint. Problems where your intuition doesn't help, or if it helps, it just doesn't get the full job done. And most of the job that needs doing in terms of predicting the behavior isn't done by your intuition. So, and of course, if you want like quantitative predictions for some application, then you need actual numbers, right? We will engage to a much greater extent in this kind of series with the complexity of the physical world than we can, in a practical sense, do in a more analytical setting. You know, it's possible to engage with a little bit of complexity in the real world using purely analytical methods, but the math gets pretty difficult, right? It's a difficult subject. What we're going to do is, in some absolute scale, pretty easy, at least at first. You know, we're going to get really far in terms of the kind of problems we can attack with relatively simple methods. You know, probably that if the whole curriculum of elementary school, high school, university wasn't so geared toward analytical methods, at least in the beginning, these numerical methods that we're going to start with would seem very, very easy. They just seem a bit strange because we're not super used to that kind of methods. Or at least, you know, that's my take on it. So what are the numerical alternatives to these kinds of analytical methods? You know, last time we saw that we could solve an actual physical problem if we had a method called root finding. And by last time I mean maybe a week ago. or z, finding x such that f of x is equal to 0 for some given function f. That's the mathematical setting for this problem. Okay, so, and we saw a really basic method for doing this. As we will kind of begin to explore, each single one of these numerical methods actually might be expanded, maybe with a few exceptions, but they might be expanded to a whole course. There's really lots of things you can add on top of the basic, or just different ways of getting to that. And we're going to keep focusing on the physics, but it's good to know that these methods run really deep, and if you need that power, it's available, and it's not scary, or at least it won't be too scary once we get a bit of practice. Okay, so today we'll start with integration, the numerical integration. Okay, the basic problem, okay, as in mathematics, how would you define that in mathematics? You have a definite integral. Okay, you basically want to compute integral of f from a to b. Okay, you might be more familiar, f of x, f of x dx from a to b, where a and b are the boundaries of your integration interval. So you want to find a number. Okay, it's called a definite integral. A number which geometrically corresponds to the area under the curve. F is one quarter of the segments that define this region, which you're calculating the area of. A and B define the sides, and the x-axis define the bottom. And if f is greater than 0 all the time, you just want to compute the area. If f sometimes goes below the x-axis, you want it's kind of this weighted area where when it's positive, it's a positive area, and when it's negative, it's a negative area, and you add or subtract to get a final number. But in physics, integration is the process that undoes differentiation, and so it's a link between things like acceleration and eventually speed and position. So because of the way certain laws of physics are set up, like I give you a force or a potential, and you must give me the trajectory or something like that. Well, integration is the ladder by which we start with force is proportional to acceleration, and we go by integration all the way down to position. That's one way of solving this problem, but there are lots of applications. For example, in quantum mechanics, whenever you're doing probability and you're trying to find the probability that something happens, you're going to do integration probably. So